Hello, my name is Mosha Pasumansky, and today I'm going to talk about really cool feature. Geospatial support in Firebolt, something that we just launched. So what is geospatial support? Basically, here we are talking about objects on the surface of Earth. And there are three main types of objects that Firebolt supports. First one is points. Points is the most common type of object. It can represent location of human, for example, carrying cell phone and sending GPS signal. Or maybe location of some object, either static like a landmark or ship or airplane, and so on. Second type of object are lines. Lines can represent things like roads and highways, rivers, and similar. They are a little bit less common. And the third type of objects are polygons. Polygons can represent boundaries of objects such as buildings, or maybe administrative boundaries like city boundaries, or borders of geographical objects like islands or continents, lakes, and so on. So now we need to talk about how we are going to model the Earth. And there are two ways to do it. First one is to build projection of the Earth to the map. So let's see how it's going to look like.
So the most common projection that we have when we're talking about geography on a map is called the Mercator projection. And it has some flaws, including but not limited to distorting objects that are near the poles. So roughly speaking, this is going to be an approximation. An island like Greenland, which is very near the North Pole, is going to look about that big. This is a poor Greenland, but it's roughly the same size as what it might look like on a map, compared to something like Africa, which is equatorial. And it might look, on a Mercator projection, to be about that big. And when you look at these two objects, they look relatively comparable in size on a map projection like the Mercator.
So that was putting objects on the map. The other way to model the Earth is to faithfully represent it as a sphere. This is the Earth. And here we have Greenland. And here we have Africa, much bigger. So in SQL, the data type which describes works with map projections is called geometry. And data type which works with the model of the Earth as a sphere is called geography. The trade-off between the two is that, of course, geography represents the reality more faithfully, more accurately, but it's easier to work with geometry. The math is simpler. So if somebody is working with local objects, like maybe within a city or city block, then geometry will be just fine. But if you need to represent things like intercontinental flight, which goes across the globe, then you really need to use geography. So in Firebolt, because we wanted to work in all scenarios, we picked the geography. Of course, implementing geography and all the math on the surface of the Earth is not simple. Luckily, there is an open source library from Google called S2, which does it excellently. It is robust, it handles all kinds of interesting cases like poles, anti-meridian, it handles floating point errors really well, But what I want to talk now about is how we use built-in indexing inside S2. So let me explain how it goes. S2 divides the entire surface of Earth into hierarchical squares. Those squares are called cells. So cell at the level 0, for example, may cover entire continent. Cell at the next level covers parts of it, and so on and so forth, until level 32, which covers squares which are approximately 9 square millimeters. I'm not going to draw 32 levels, but let's add a couple more. Each cell in S2 is represented by a 64-bit integer. And the interesting thing about them is that operations which check the containment on cells are super efficient because they pretty much do bit manipulations. Now I'm going to show you how we use those indexes to implement one of the PostGIS compatible functions, stcovers. And I will use the most common example when we want to find out which points are inside polygon and which points are outside. So for example, polygon may represent interesting area like a store or port, and points can represent locations of people walking into store or ships getting into port. And we need to find out which ones of those points are inside the area we're interested in. So let's take an example. So this is the example of polygon, and it could be pretty complex. And now usually we have only a small number of fixed polygons that we want to check containment against, but many different points. So first we compute exterior cover of this polygon. Exterior cover is number of S2 cells which completely cover the polygon. The number of cells is an interesting consideration because the more cells you use, the more precise your cover becomes, but then you need to do more comparisons. And the less you do, the less cells you choose, the less comparisons to do, but the less precise the cover is. We start with 8 cells because 8 64-bit integers nicely fit into processor cache line. For the sake of the illustration, I'm going to show only 2 cells here, cover with 2 cells. So this is 1, and this is 2. And you can see that together, those 2 cells cover the polygon completely. Now, when we have many points stored in Firebolt table, we already pre-computed their cover. Actually pre-computed for any shape, but for points, it's especially simple because point is always contained or almost always within a single cell. Let's pick this point here. Its cover is so small that you cannot distinguish it from the point itself. Now we do this super fast integer comparison, bit manipulation, and we see that this point is outside of exterior cover of the polygon, so it has no chance to be inside. So we reject this point right away. Okay, what about points like that? This point is inside exterior cover. It might be inside polygon, might be outside. In this case it is outside, but we need to do pretty expensive operation to check for sure. So the next optimization we do, we also compute interior cover of the polygon. Those are S2 cells which are completely inside. And now we check. If the point is inside interior cover of the polygon, it is for sure contained by the polygon. So let's go back to this point. it's inside exterior cover, but not inside interior cover. So we don't actually know. We still need to do the expensive check. And this is where Firebolt adaptive runtime kicks in. When we see that we have many of those points which kind of fall in between, what we do is we dynamically change number of cells for both exterior and interior cover. So instead of having just two very coarse grain ones, we pick many more detailed ones. Something like that. And now you see this point, it falls outside of the new exterior cover, so we can prune them better. And now let's see how it works in a demo. So the data we're going to use for this demo is data on car accidents in the US over the 5 or 6 years. So we'll have this table. Let's see how it looks like. It has a lot of details about every accident, but the interesting ones that we're looking here are start and end of the accident. So here we see column end, and it's of type geography, and here column start, and it's also of type geography. There are about 7 million rows in this table, and we're running it on smallest possible engine. So to show geography working, we built a web app to demonstrate it. Okay, well, who am I kidding? We didn't build the web app. In 2025, nobody builds web app. We actually went to AI and asked it to build the app for us. And amazingly, it did. All we needed to do was to add credentials to log into Firebolt. Here's the web app running with some JavaScript visualization with Python connecting to Firebolt. So let's see. Let's say what we want to do is to look at accidents which are happening around Central Park in New York. I see the Central Park. Let's draw a polygon around it. And we're going to use the function stcovers, the one that we just talked in the video. So database contains locations of all accidents, and this polygon, this rectangle that we put, represents polygon, and we want to see all the accidents that happened within of it. Here you can see the query that got generated. We see that the polygon itself is a constant, in this case represented using GeoJSON, and we're using stcovers function between this polygon and start point of the accident. And this all the accidents looks like there are more on the west side than on east side, and we can zoom and look at them, and everything that we just talked about, like all the covering cells, all the adaptive runtime to pick up the number of them, they worked pretty well because the response was pretty quick here. Today, we saw a little bit of Firebolt geospatial capabilities. If you want to learn more, you can read our technical blog, which goes in much more depth, or you can sign up and try for yourself. The links are in the description to this video. Thank you for watching.